Inside your computer, there's a silent partnership humming along between two incredibly powerful brains. On the surface, they seem pretty similar, right? They're both silicone, they both crunch numbers at mind-boggling speeds, but they are built on two fundamentally different philosophies. One is this brilliant, lightning-fast jack-of-all-trades. The other, it's a specialist in just massive, brute force parallelism. And understanding that difference, well, that's the key to pretty much everything your computer can do.
So here's the big question, the one that this is all about. Why do we even have both? Why can't the generalist just, do the specialist job? Or why can't that massive specialist just run the whole show? The answer to that question reveals one of the most important fundamental divides in all of modern computing. Okay, let's really get into it. All right, so to really get our heads around the difference between a CPU and a GPU, first we have to understand these two almost warring philosophies they were designed to serve, and that's latency versus throughput. We're not just talking about different designs here, we're talking about completely different ways of thinking about how to get work done.
And this slide just nails the analogy perfectly. Think of your CPU as the master head chef in some fancy kitchen. Their entire goal is to take one super complex recipe with tons of steps and execute it flawlessly from start to finish, as fast as humanly possible. Now the GPU, that's the army of kitchen assistants. Their job isn't to cook the fancy dish. Their job is to do one simple repetitive task, like, say, chopping 1,000 onions, all at the exact same time. One cares about the speed of a single task, the other cares only about the total volume of tasks.
So that brings us to the CPU's core obsession. It's all about reducing latency. Now, latency is just a fancy word for the delay between when you start a task and when it finishes, and the CPU is absolutely obsessed with it. Every single time you click an icon, open a program, surf the web, you need a response right now. That's the CPU's world, handling all these random one after another tasks with the lowest possible delay.
The GPU, on the other hand, plays a totally different game. It honestly couldn't care less how long one little task takes. It's built for throughput, which just means jamming as much total work as possible into every single second. And this design philosophy comes straight from its original job, graphics. It had to figure out the color, the lighting, and the position from millions of individual pixels on your screen, and it had to do it 60 times a second. Each little pixel calculation is simple and totally independent of the others, making it the absolute perfect job for that army of assistants.
Okay, so we've got the two philosophies. We get the what. Now let's dig into the how. How these ideas are literally baked into the silicon itself. Because this isn't just a software thing. No, it's a deep, fundamental split in their hardware design. A split that was actually forced on them by a very real physical problem.
So back in the mid-2000s, engineers hit what they call the power wall. They literally couldn't make chips faster just by cranking up the speed anymore, because they'd get so hot they'd just melt. They had to get creative to find more performance. And this is the exact moment where the CPU and GPU went down two totally different paths. The CPU decided to get smarter. The GPU, it decided to get bigger, a lot bigger. And this table just lays it all out, clear as day. Look at this. A modern CPU might have, say, 16 really powerful cores. A GPU, it can have over 16,000 simple ones. And look at where they spend their precious silicon real estate. The CPU uses most of its transistors on smart stuff, huge caches to keep data super close, and really complex logic to try and predict what you're going to do next. But the GPU, it throws all that out the window and dedicates almost every single transistor to raw calculation engines, what we call ALUs. It sacrifices all that cleverness for just overwhelming brute force numbers. Their whole strategy for dealing with memory is completely opposite, too. For a CPU, having to wait 100 nanoseconds for data to come from your main RAM, that's a 5-alarm fire. It's a catastrophe that it spends billions of transistors trying to prevent with all those caches. For a GPU, waiting 500 nanoseconds? That's just Tuesday. It's totally normal. See, it doesn't try to reduce the delay, it just hides it. The second one group of its thousands of tasks has to wait for data, the GPU's hardware scheduler just instantly swaps in another group that's ready to go. It's designed to always have something to do, which lets it tolerate delays that would absolutely bring a CPU to its knees. Okay, so we've got the philosophy, we've got the architecture, but what does this all actually mean in the real world? Like when you put these two different brains to the test on a job that's perfect for this kind of parallel work, the performance difference isn't just big, it is frankly kind of insane. And the perfect test case for this is something called matrix multiplication. Now, I know that sounds super academic, but trust me, this is the mathematical engine behind almost everything cool in tech right now. From training massive AI models to rendering the incredible graphics in a video game, it all comes down to this. And the best part? It's a job that is just begging to be broken up into a million tiny parallel pieces. It is the perfect arena for a CPU versus GPU showdown.
So, some recent research laid out the results, and they're pretty eye-opening.
Especially when you start to scale the problem up.
All right, so using data from that study, running on a totally standard gaming laptop, we see the GPU's lead just explode. For a pretty small problem, it's already 125 times faster. That's wild. But as the problem gets bigger, that gap stretches to 360 times, and for a really large matrix, the kind you see in AI all the time, the GPU is almost 600 times faster. Let me just say that again, 600 times faster. That's not a small improvement. That's the difference between a calculation taking 10 minutes or just 1 second.
Okay. But you might be thinking, hold on, is that really a fair fight? I mean, we just compared a massively parallel GPU to a CPU running on just one little thread. So what happens if we let the CPU use all of its cores and we optimize the heck out of it? Well, the study did that too. And even in a totally fair apples-to-apples fight, the GPU is still 45 times faster on the biggest problem. That right there shows you that for the right kind of work, there is simply no substitute for the GPU's throughput-first design.
So with numbers like that, you got to ask, why aren't we just using GPUs for literally everything? And that brings us right back to our original question. Why can't you just swap them? Well, it turns out there's some massive roadblocks, both in pure logic and in cold, hard physics.
So trying to run your operating system on a GPU would be an absolute disaster. And here's why. Two big reasons. First, something called branch divergence. Your OS is just full of if this happens, do that decisions. But on a GPU, if one of its little workers needs to do this and another in the same group needs to do that, the whole group is forced to run both paths one after the other. Its parallel superpower just vanishes. Second, there's pointer chasing. An OS is basically on a constant scavenger hunt, looking up data addresses in memory. And you can't find the next clue until you've solved the current one. It's a fundamentally sequential job that a GPU is just terrible at.
And beyond all that logic, there's an even simpler, more fundamental rule. When you hit the power button on your computer, the very first thing that wakes up is the CPU. It's the master controller. It runs that initial boot up sequence that gets everything else talking, the memory, the drives, and yes, the GPU. A computer can boot up just fine without a GPU, but without a CPU, it's just a dead box of silicon. It can't even start.
And just in case you were still thinking about physically swapping them, here's a very serious warning from the folks at XDA developers. The 8-pin power cables for your CPU and your GPU, they look almost identical, but they're wired in complete opposition to each other. If you force the wrong one in, you create a direct short circuit. Best case scenario, your power supply just clicks off. Worst case, you've just fried your most expensive components. They are physically and electrically incompatible by design.
So here's the real takeaway. This was never a competition. The CPU and the GPU aren't rivals trying to take each other's jobs. No, the future isn't about one replacing the other. It's all about making their partnership even tighter, even more efficient. And we're already seeing this happen. There's this whole field called heterogeneous computing that's all about writing smarter software that knows exactly which brain is best for which part of a task. We're even seeing a third brain pop up, the DPU, or data processing unit, whose only job is to handle boring networking and storage tasks, freeing up both the CPU and GPU to do what they do best. And maybe the biggest deal of all is a new standard called CXL. It's basically creating a shared pool of memory, so both processors can work on the same data at the same time without having to make slow, painful copies back and forth.